Right now, deep inside the most advanced laboratories on Earth, physicists are conducting experiments that could rewrite reality itself, because hidden within quantum mechanics, encoded in the mathematics of black holes, and woven into the very structure of space-time, lies a revelation so staggering it defies belief. Our universe, the stars, the galaxies, even you might not be what they seem. We could be living inside something far stranger. A projection, a hologram, a simulation. If you're ready to follow this mystery to its edge, hit subscribe. You'll want to see where this journey leads. Now, let's begin. In 1974, Stephen Hawking made a discovery that shattered the foundations of physics. He found that black holes aren't eternal. They slowly evaporate, releasing radiation until they vanish completely. It sounded simple enough, but it unleashed a paradox that still haunts science half a century later. Here's why this matters to you. The universe obeys one sacred law. Information can never be destroyed. Burn a book, and its words still exist, scattered through heat, smoke, and ash. Physics demands that every particle, every bit of data, is accounted for. But black holes seem to break that law. Anything that falls beyond the event horizon, the point of no return, is erased from existence. And as the black hole evaporates through Hawking radiation, it releases only random noise, not the encoded memory of what it consumed. The information is gone. Einstein's theory of relativity said that was fine. Quantum mechanics said it was impossible, and thus began one of the greatest conflicts in the history of science. Two perfect theories, locked in a cosmic contradiction, both pointing to the same unsettling possibility that reality itself might not be as real as we think. Physicists went searching for a solution. What they found was even stranger. In 1993, a Dutch physicist named Gerrit Hoof proposed something radical. What if the information never really fell inside the black hole? What if it stayed on the surface the whole time, encoded on the event horizon like data on a hard drive? This is a confirmed theory in modern physics. Leonard Susskind developed it further. He showed that everything inside a black hole could be described by information on its two-dimensional surface, just like a hologram. A hologram looks three-dimensional, but all the information creating that image lives on a flat surface. The depth is an illusion. Here comes the part that changes everything. If this works for black holes, why not for the entire universe? Think about what this means. Every atom in your body, every star burning across space, every thought in your mind, all of it might be information, encoded on a distant boundary, a cosmic event horizon trillions of miles away. We think we live in three dimensions. We think we move through real space, but we could be projections, holographic images created by data existing somewhere else entirely. This is not science fiction. This is the holographic principle, a leading theory in theoretical physics. Scientists have run computer simulations testing this idea. In 2013, Japanese physicist Yoshifumi Yakutake calculated the internal energy of a black hole using string theory. Then he calculated the energy of a lower dimensional universe with no gravity. The numbers matched perfectly. Juan Maldacena at Princeton called it a correct computation. The math works, but nobody expected what came next. When physicists looked closer at our own universe, they found evidence everywhere. Strange patterns that only make sense if reality is holographic. And that was just the beginning of the problem. You are not where you think you are. According to the holographic principle, the three-dimensional universe you experience is actually encoded on a two-dimensional boundary infinitely far away. Everything you see, touch, and feel is a projection from this distant surface. This theory is currently unproven, but widely accepted among theoretical physicists. It solves the black hole information paradox perfectly, but it also suggests something deeply unsettling about reality. Space might not be fundamental. Imagine watching a movie. The characters seem to move through three-dimensional space. They walk forward and backward, up and down, but the actual information creating this scene lives on a flat screen. The depth is manufactured by the projection. Our universe could work the same way. The holographic principle says that everything happening in a volume of space can be completely described by information on the boundary of that space, like a room where everything inside is determined by equations written on the walls. In 10, generated by something simpler and flatter. You are an equation being computed. Recent studies have found more evidence. In 2017, researchers published findings in Physical Review Letters showing substantial support for a holographic universe. They analyzed irregularities in the cosmic microwave background, the afterglow of the Big Bang. The patterns matched holographic predictions, as well as they matched standard cosmology. Leonard Susskind at Stanford said these results confirmed something physicists were fairly sure had to be true. The thermodynamics of certain black holes can be reproduced to permit a lower dimensional universe. But our universe is not identical to the models they tested. The cosmos we inhabit is de Sitter space, not anti-de Sitter space. Scientists are still working toward a perfect match. If they succeed, it will prove our universe is truly a hologram. And once you accept that reality is projected information, a darker question emerges. Information encoded by what? Projected by whom? The math has no answer for that. In 2013, a team of Japanese physicists did something that should have been impossible. They calculated the properties of a black hole 2 different ways. One used string theory in 10 dimensions. The other used quantum mechanics in just 1 dimension. 2 completely different universes, 2 completely different sets of physics. The results were identical down to the decimal point. Every property matched: the internal energy, the entropy, the position of the event horizon, even the effects of virtual particles constantly popping into and out of existence. Juan Maldacene called it a correct computation. Leonard Susskind said it was the first numerical proof of something physicists had believed but never confirmed, that fundamentally different realities can be perfectly equivalent. This is hard, experimental evidence, not speculation. Yoshifumi Hayakutake led the research team at Ibaraki University. They used supercomputers to simulate both universes simultaneously. The calculations took years. When the numbers finally came in, they revealed something profound. 2 universes that appear nothing alike can describe the same physical system, like 2 languages translating the same sentence perfectly. But here is what makes this discovery so disturbing. If completely different realities can produce identical results, how do we know which one we live in? We could be inhabitants of the higher dimensional universe with gravity, or we could be living in the lower dimensional universe without it. Both would feel exactly the same to us. The math cannot tell the difference. Think about a video game character. That character exists in a 3-dimensional world from its perspective, but the actual code runs on a processor somewhere else. The world the character experiences is not where the computation happens. We could be the same, experiencing a projected reality, while the real computation occurs in a totally different space. Scientists have expanded these simulations since 2013. They have tested other configurations, different numbers of dimensions, different types of force. Every test confirms the same thing: holographic equivalence works. Physicist Netta Engelhardt at MIT studies these dualities. She said that knowing you are talking about the same physics from 2 perspectives is incredibly powerful. Sometimes problems impossible to solve in one description become trivial in the other. Researchers have used this to study black hole evaporation, quantum entanglement, and the nature of space-time itself. Every discovery strengthens the case for holography. But these simulations revealed something else, something nobody expected. The holographic universes that work mathematically are simpler than our universe. They have fewer dimensions, less complexity, like seeing a high-resolution image and discovering it was generated from a much smaller file. This suggests our universe might be compressing information, running on some kind of efficiency algorithm, minimizing computational resources, while maximizing output, exactly like you would design a simulation that needs to run on limited hardware. The Japanese simulations proved holographic universes are possible. They work perfectly in theory. Scientists are now looking for evidence that our universe is actually one of them. And the first clues appeared in the most unexpected place, a number that should not exist. There is a number in physics so wrong it should have destroyed the universe. It is called the cosmological constant. It controls how fast space itself is expanding. Right now, the universe is accelerating outward. Galaxies are moving apart faster and faster. The cosmological constant explains why scientists measured its value carefully. It is a tiny positive number, almost zero, but not quite. Then they tried to calculate what it should be using quantum field theory. The prediction came back 120 orders of magnitude too large. Let me put that in perspective for you. Imagine you expected something to be 1 inch long. You measure it and find out it is actually 1,000 billion 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 miles long. Instead, that is how wrong the prediction was. This is the worst prediction in the history of physics. Physicists call it the cosmological constant problem. Some call it the vacuum catastrophe. Either name works because both capture the same impossible situation. Our best theory of quantum mechanics predicts a universe that cannot exist. If the cosmological constant were even close to the predicted value, space would expand so violently that atoms could never form. Stars would be impossible. Galaxies would never exist. The universe would rip itself apart in less than a second after the Big Bang. But here we are, living in a stable universe with a cosmological constant so precisely balanced, it seems designed. Physicist Paul Davies explained it this way: the vacuum of space contains energy. Quantum mechanics demands it. This vacuum energy should accelerate the expansion of the universe catastrophically, but something else must exist, a negative value almost exactly as large as the vacuum energy. The two cancel out to create the tiny positive number we observe. This requires precision beyond anything we have ever seen in nature. Here is where it gets worse. The cosmological constant depends on two other universal constants, the gravitational constant and the weak force constant. If either of these changed by just 1 part in 1050, the delicate balance would shatter. 1 part in 10 to the power of 50 is a number so small it defies comprehension. It would be like balancing a pencil on its point and having it stay perfectly vertical for billions of years. And not just one constant. Multiple constants had to land in impossibly narrow ranges simultaneously. Many physicists believe this fine-tuning points to a multiverse, countless universes with different constants, and we just happen to exist in the rare one that works. This is a popular theory, but completely unproven. Others think it suggests a simulation, programmers adjusting parameters until they got a stable universe. This is also unproven, but disturbingly plausible. Here is what we know for certain. The cosmological constant is real. The predictions are real. The impossible precision is real. Something forced our universe to have exactly the right value. The odds of this happening by chance are effectively zero. Either there is a deeper law of physics we have not discovered yet, or something deliberately set these numbers. The cosmological constant is not the only fine-tuned value. There are dozens more, each one balanced on the same knife edge. Our universe runs on 26 numbers that should not work. These are the fundamental constants of physics: the strength of gravity, the mass of an electron, the speed of light. Each one had to land in a precise range for reality to function. Change any of them slightly, and the universe collapses. Physicist Fred Adams studied what happens when you alter these constants. He ran simulations creating alternate universes with different value. Almost all of them were dead on arrival. No stars, no planets, no possibility of life. The standard model of particle physics contains 25 freely adjustable parameters. General relativity adds one more, the cosmological constant. These numbers are not predicted by any deeper theory. They just are what they are. But here is the problem. The range of possible values for each constant is enormous. Some could theoretically be infinite. Yet, Every single one landed in the narrow band where complex structures can exist. Let me show you what I mean. The strong nuclear force holds atomic nuclei together. If it were 5% stronger, d protons would be stable. 2 protons could bind without a neutron. This sounds harmless, but it would destroy everything. Hydrogen would fuse so easily that the entire universe would burn through its fuel in minutes after the Big Bang. No hydrogen means no water, no long-lived stars, no chemistry. If the strong force were 5% weaker, deuterium would not form. This is the nucleus with 1 proton and 1 neutron. Without it, heavier elements could never be created in stars. The universe would be nothing but hydrogen forever. The electromagnetic force is equally critical. Too strong, and atomic bonds would be too tight. Molecules could not form. Too weak, and atoms would fall apart. Chemistry would be impossible. The weak nuclear force controls radioactive decay and fusion in stars. Change it slightly, and stars either burn too fast or never ignite at all. Gravity is the most sensitive. Paul Davies calculated that if the gravitational constant changed by 1 part in 10 to the power of 50, stars would either become too hot and burn out instantly or never form at all. 1 part in 10 to the power of 50, that number keeps appearing. This is precision, far beyond anything in human technology. We cannot build machines this accurate. We cannot measure things this precisely. Yet nature somehow achieved it across multiple independent constants. The electron mass is another critical value. If electrons were slightly heavier, atoms would be too small. If lighter, too large. Either way, chemistry breaks down. The ratio between the proton mass and the electron mass is 1036. This specific ratio allows stable atoms to exist. Change it by a few percent, and matter cannot form. Scientists like Robin Collins have documented these examples extensively. He argues that the cumulative improbability of all these constants landing in the right range by chance is astronomically small. Lawrence Krauss disagrees. He says we may discover deeper laws that explain why these constants have their current values. Once we understand them, they may not seem fine-tuned anymore. This is currently an open debate in physics. But here is what nobody disputes. Right now, with our current understanding, the universe appears impossibly well calibrated. Every constant balanced perfectly, every ratio precise. It looks exactly like someone adjusted the setting. When you examine how these constants interact, the case for design gets even stronger. Let me tell you about the most terrifying number in physics. 1 part in 10 to the power of 50. This is how precisely the gravitational constant had to be set for stars to exist. Not approximately correct. Not close enough. Exactly this value, within a margin so small, it defies imagination. Write out the number 10 to the power of 50. That is a 1 followed by 50 zeros. Now imagine dividing something into that many parts. Change one single part. Just one. And the universe dies. If gravity were slightly stronger, stars would collapse into black holes almost immediately after forming. They would burn through their fuel so fast that life could never develop. Planets would be crushed by their own weight. The universe would be a graveyard of dead matter and radiation. If gravity was slightly weaker, stars would never ignite at all. Matter would drift apart. Gas clouds could never compress enough to trigger fusion. No starlight, no heat, no heavy elements created in stellar cores. The universe would remain a cold, dark fog of hydrogen forever. This is a confirmed calculation. Physicist Bernard Carr studied these scenarios extensively. He found that the habitable range for the gravitational constant is astonishingly narrow. The universe we observe sits right in the middle of this tiny window, but gravity's fine-tuning connects to everything else. Remember the cosmological constant from earlier? It depends partially on the gravitational constant. Change gravity, and you automatically throw off the cosmic expansion rate. The same applies to star formation, galaxy clustering, and planetary orbits. Everything locks together in a web of dependencies. Think about our sun. It has been burning steadily for over 4.5 billion years. This stability is not common. It requires gravity strong enough to hold the star together, but weak enough that fusion happens slowly. Most stars either explode or fade quickly. Our sun hit the perfect balance. So did billions of other stars in the habitable zones of their galaxy. Here is something even stranger. The gravitational constant determines how matter clumps together on cosmic scales. Too strong, and the universe would have collapsed back into itself shortly after the Big Bang. Too weak, and galaxies would never form. Observations confirm that gravity is calibrated to allow maximum structure formation. The universe is old enough for stars to forge heavy elements, young enough that stars still burn, lumpy enough to create galaxies, smooth enough to avoid collapsing. Every parameter sits at the optimal value. Physicist Roger Penrose calculated the odds of the universe's initial conditions being this precise. He arrived at one chance in 10 to the power of 10 to the power of 12. This number is so large, it has no physical meaning. There are not that many particles in the observable universe to count it. Some scientists point to the anthropic principle. We observe these values because we could not exist in a universe with different values. This is true, but does not explain why any universe has these values in the first place. Others invoke the multiverse, infinite universes with random constants, and we exist in one of the rare winners. This remains unproven and possibly unprovable. And then there is the uncomfortable third option, the one that keeps appearing in the data. Someone set these numbers deliberately, adjusted them with impossible precision, built a universe that worked, whether that someone is a deity, an advanced civilization, or something else entirely. The question remains unanswered, but the precision is undeniable. There is a force that holds you together. Literally, the strong nuclear force binds quarks into protons and neutrons, then binds those protons and neutrons into atomic nuclei. Without it, matter would instantly disintegrate into elementary particles. You would not exist. Nothing would. But this force operates on an edge so sharp that a tiny shift in either direction destroys everything. Scientists have calculated the boundaries. They are terrifyingly narrow. If the strong force were 2% stronger, something catastrophic happens. D protons become stable. This is a nucleus with 2 protons and no neutrons. In our universe, D protons cannot exist. 2 protons repel each other too strongly, but increase the strong force just a little, and that repulsion is overcome. Protons bind directly to other protons. This sounds harmless. It is apocalyptic. With stable D protons, hydrogen fusion becomes easy. Too easy. In the first moments after the Big Bang, when the universe was still incredibly hot and dense, all the hydrogen would fuse instantly. Every single proton would combine with another proton. The universe would convert all its hydrogen into helium in less than 3 minutes. Then the fusion would stop. No fuel left. Fast forward billions of years. No hydrogen means no water. Water is 2 hydrogen atoms and 1 oxygen atom. Without hydrogen, water cannot exist. No oceans, no rain, no life. Stars need hydrogen to burn. They fuse it gradually into heavier elements over billions of years. This slow burn creates stable energy output. But with all the hydrogen gone, stars would either never form or burn out immediately. The universe would be sterile. Now consider the opposite direction. What if the strong force were 2% weaker? Deuterium becomes unstable. This is a nucleus with 1 proton and 1 neutron. It is the first step in building heavier elements. Stars fuse hydrogen into deuterium, then deuterium into helium, then helium into carbon, and so on up the periodic table. But if deuterium cannot hold together, this entire chain breaks. Stars cannot create anything heavier than hydrogen. The universe would be one element forever. No carbon, no oxygen, no iron, no heavy atoms at all. Every single element that makes up your body requires the strong force to be precisely where it is. Carbon forms because of a specific resonance in the strong force. A slight change, and carbon becomes impossible to create. Physicist Fred Hoyle famously predicted this carbon resonance before it was discovered. He said it had to exist, or life would be impossible. When experiments confirmed it, Hoyle was shaken. He said it looked like someone had monkeyed with the laws of physics. The strong force also determines nuclear stability. Too weak, and atomic nuclei fall apart. Too strong, and exotic particles that do not exist in our universe become common. Scientists at CERN study the strong force constantly. They smash particles together at near light speed to measure how quarks interact. Every experiment confirms the same thing. The strong force is exactly the strength it needs to be, not approximately exact. We are talking about a parameter that could theoretically have any value across an enormous range, yet it landed precisely in the sweet spot where chemistry works, where stable elements exist, where complexity is possible. Change it by a couple percentage points, and existence ends. This is not the last fine-tuned force. There are others equally critical, and when you look at how they all work together, the picture becomes even more unnerving. A physicist at the University of Portsmouth believes he has found evidence we live in a simulation. His name is Melvin Vops. His argument centers on a law he formulated called the second law of interdynamics. This law describes how information behaves, and according to Vopson, the universe is optimizing information the same way computer code does. Let me explain what this means. In computer science, compression is essential. Large files are reduced in size without losing important data. This makes programs run faster and use less memory. Every video you stream, every image you download has been compressed. Vopson noticed something strange. Information systems in nature decrease in entropy over time. This should not happen. The second law of thermodynamics says entropy always increases, disorder always grows. Yet information systems seem to follow a different rule. They become more ordered, more efficient, more compressed. He tested this idea by studying mutation patterns in viruses, specifically the SARS-CoV-2 virus that causes COVID-19. The virus mutates constantly as it replicates. According to traditional evolutionary theory, these mutations should be random. But Vopson found a pattern. The mutations were not random. They were optimizing information entropy, making the genetic code more efficient, compressing it. This is a published finding in the journal AIP Advances. The data shows a correlation between information and mutation dynamics that should not exist if mutations are truly random. Think about what this implies. Biological systems are behaving like software being debugged, finding inefficiencies and eliminating them, streamlining code. But viruses do not have programmers. They have no conscious intention to optimize, yet they do it anyway. Vopson argues this compression happens everywhere. In atomic physics, electrons arrange themselves to minimize information entropy. In cosmology, the universe expands without gaining or losing heat. This requires total entropy to remain constant. Thermodynamics says entropy should increase. But Vopson proposes another type of entropy exists, information entropy. It decreases to balance the increase in thermodynamic entropy. Now, here is where it connects to simulation theory. If you wanted to simulate a complex universe like ours, you would need enormous computational power, more power than might be available. So you would compress the data, optimize it, find mathematical shortcuts that produce the same results with less processing. This is exactly what the second law of interdynamics describes. A universe that compresses its own information to reduce computational load. Physicist Paul Davies has written about this. He notes that the universe seems to follow the path of least computational action. Nature finds the most efficient solutions, the shortest routes, the minimal energy states. This principle appears in classical mechanics as the principle of least action. Particles take the path that minimizes a quantity called action. It is one of the most fundamental rules in physics. But why would nature care about efficiency? Why does the universe consistently choose the least complicated option unless it is running on a system with limited resources? Vopson believes The second law of interdynamics could prove we live in a simulation. A universe that actively compresses its own data is a universe designed to run on a computer. This is his theory. It remains unproven and controversial. Many scientists disagree with his conclusions. They argue that information behavior can be explained without invoking simulations, but the data itself is not disputed. The universe does appear to optimize information. It does run on compression algorithms. Whether this proves simulation or reveals a deeper law of nature is still unknown. Either way, something is managing the computational resources of reality, and the optimization becomes even more obvious when you look at entropy itself. There is a law in physics that nothing violates, except the universe seems to be violating it constantly. The second law of thermodynamics says entropy always increases, disorder always grows. You can never spontaneously organize a system without adding energy from outside. This is why your room gets messy, but never cleans itself. Why ice melts, but water does not freeze without a refrigerator. Entropy is the arrow of time. It points in one direction toward chaos, but information entropy appears to point the opposite way. Melvin Vopson documented this in his research. He found that information systems become more organized over time, more efficient, less random. This violates everything we know about thermodynamics, unless there is a balancing act happening. Vopson proposes that as thermodynamic entropy increases, information entropy decreases. The two balance each other perfectly. This keeps the total entropy of the universe constant, which matches what we observe. The universe is expanding without gaining or losing heat. This should be impossible. Expansion should generate entropy, but measurements show total entropy staying level. Where is the missing entropy going? Vopson says it is being converted into information order. The universe is reorganizing its data while its physical state becomes more disordered, like a computer defragmenting its hard drive while the program continues running. Here is where this becomes truly strange. This kind of balancing act is exactly what happens in simulations. When you play a video game, the graphics engine constantly optimizes. It renders only what you can see. It compresses textures. It reduces polygon counts in distant objects. The simulation maintains performance by decreasing information complexity wherever possible. Your computer has limited processing power. The game must run efficiently, or it crashes. So the code is designed to minimize computational load. If our universe is a simulation, it would face the same constraints: limited processing power, limited memory. The system would need to compress data constantly to keep running. And that is exactly what we observe. Physicist John Barrow studied this from a different angle. He looked at mathematical symmetries in nature. Symmetry is a form of compression. Instead of storing information about every individual particle, nature stores patterns, rules that apply to groups. This is how software works. Instead of defining every pixel separately, you define a function. The function generates all the pixels automatically. Much more efficient. Nature does this everywhere. Physical laws are compressed information. The equation for gravity applies to every massive object in the universe. You do not need separate rules for each star and planet. One equation covers everything. FEMA, EEMC², the Schrödinger equation. All of these are compression algorithms. They generate infinite specific cases from finite general rules. The universe runs on elegant mathematics because elegant mathematics is the most compressed form of information. But thermodynamics says this should not happen. Information should become less organized, more random. Yet physical laws remain perfectly consistent across billions of light years and billions of years of time. Something is maintaining the order. Scientists have different explanations. Some say deeper physical principles exist that we have not discovered. These principles naturally create the balance between information and thermodynamic entropy. Others say the multiverse explains it. We exist in a universe where the laws happen to balance correctly. Other universes have different rules. And then there is simulation theory. The universe compresses information because it is running on a computer with finite resources. The second law of infodynamics is real code optimization happening in real time. We cannot prove which explanation is correct yet, but the data keeps pointing in one direction. The universe behaves like optimized software, and nowhere is this more obvious than in quantum mechanics, where reality itself changes based on what you observe. This is the experiment that broke common sense. It is called the double-slit experiment. Thomas Young first performed it with light in 1801. When physicists repeated it with electrons in the 20th century, they discovered something impossible. Particles behave differently depending on whether you watch them. Here is the set. You fire electrons one at a time at a barrier with two narrow slits cut into it. Behind the barrier is a detection screen. You expect the electrons to pass through one slit or the other and hit the screen behind that slit. Instead, you get an interference pattern, alternating bands of high and low electron density. This pattern is impossible if electrons are particles. It only makes sense if electrons are waves. Waves passing through both slits simultaneously, then interfering with themselves on the other side. But electrons are particles. We fire them individually. We detect them as individual points on the screen. They cannot be in two places at once, except they can, and they are. When you do not measure which slit the electron passes through, it behaves like a wave. It goes through both slits, creates interference. Now place a detector at the slits, something that records which path the electron takes. Run the experiment again. The interference pattern vanishes. Suddenly, the electrons behave like particles. Each one passes through only one slit, no interference, just two bands on the screen directly behind the slits. The act of observation changed the outcome. This is confirmed experimental data. Scientists have repeated this experiment thousands of times with photons, electrons, atoms, even large molecules. The result is always the same. Watch the particle, and it acts like a particle. Do not watch, and it acts like a wave. Richard Feynman called this the central mystery of quantum mechanics. He said it contains everything strange about the quantum world compressed into one demonstration. But it gets weirder, much weirder. Scientists tried leaving the detector in place, but not recording the data. The detector measures which slit the electron passes through, but nobody looks at the result. No human observer involved. The interference pattern returns. The electrons know whether the information is being stored. If the measurement is recorded permanently, even if nobody watches, the electrons act like particles. If the measurement happens but is not saved, they act like waves. This should not be possible. The electron has no awareness. It is not conscious. How does it know whether a detector is recording data? Some physicists invoke the Copenhagen interpretation. Observation collapses the wave function. Before measurement, the electron exists in a superposition of all possible states. After measurement, it becomes one definite state. But this raises another question. What counts as observation? Does it require consciousness? Or is any interaction with a measuring device enough? Experiments suggest consciousness is not required. Any permanent record of the electron's path destroys the interference pattern. This could be a detector, a camera, or even air molecules that scatter differently based on which path the electron took. The common factor is information. If information about the path exists anywhere in the universe, the wave function collapses. This is confirmed by quantum decoherence theory. Particles lose their wave properties when they become entangled with their environment. The environment acts as a permanent record, but here is the truly disturbing part. Some interpretations of quantum mechanics say the particle does not have a definite path until you measure it. The act of measurement does not reveal where the particle was. It determines where the particle was. You are not observing reality, you are creating it, and delayed choice experiments make this even more unsettling. In 1978, physicist John Wheeler proposed an experiment so strange that most people assumed it was just a thought experiment, something impossible to actually perform. Then in 2007, scientists did it, and the results were terrifying. Wheeler asked a simple question: What if you could decide whether to measure a particle's path after it already passed through the slits? Could your future choice affect the particle's past behavior? According to classical physics, this is nonsense. The past is fixed. What happened already happened. Your decision now cannot change what occurred before. Quantum mechanics says otherwise. Elaine Aspect and his team at the Institut d'Optique in France performed Wheeler's delayed choice experiment with single photons. They used beam splitters instead of slits. The setup allowed them to randomly decide whether to recombine the photons' paths or leave them separate. Here is the critical part. They made this decision after the photon had already passed the first beam splitter, after it should have already chosen to behave as a wave or a particle. If they recombined the paths, interference appeared. The photon had behaved like a wave, passing through both paths simultaneously. If they left the paths separate, no interference, the photon had behaved like a particle, taking only one path. Their future choice determined the photon's past behavior. Confirmed experimental result published in Science. Andrew Truscott at Australian National University repeated this experiment in 2015 using helium atoms instead of photons. He used a quantum random number generator to ensure the decision was truly unpredictable. The atom could not know in advance which measurement would be performed. Same result. The measurement choice made after the atom passed through the apparatus determined which path it had taken before the measurement existed. This forces us to accept one of two conclusions. Either particles do not have definite properties until they are measured, even retroactively, or information can travel backward in time. Neither option makes sense. Both are supported by evidence. Most physicists favor the first explanation. The particle's path is undefined. Until measurement, it exists in superposition. When you measure, you collapse the superposition and retroactively define which path the particle took. But this implies the past is not fixed. Events that already occurred can be altered by measurements you make later. Reality is not a series of definite moments progressing forward. It is a probability cloud that crystallizes only when observed. You are not moving through time. You are collapsing possibility space. This connects directly to simulation theory. In a video game, the environment does not fully exist until you look at it. The code renders only what appears on screen. Step into a new room, and the game loads that room's data. Step back out. It may unload. The past is not stored permanently. Only the current state and future possibilities exist in memory. Our universe could work the same way. The past is not a massive database of every event that ever occurred. It is a compressed history that gets generated retroactively when you measure something. This would explain delayed choice experiments perfectly. The particle's path does not exist in memory until you check. When you perform the measurement, the universe calculates what path is consistent with all prior measurements and assigns that path retroactively. Maximum data compression, minimum computational load. But we are not done with quantum strangeness yet. The next phenomenon is even harder to explain without invoking something deeply weird about reality. Particles that communicate faster than light across the entire universe and do it instantaneously. Einstein hated this idea. He called it spooky action at a distance. He was wrong. Take two particles and link them together, then separate them by millions of miles. Measure one particle, the other instantly knows what happened. This is quantum entanglement. It is real, it is confirmed, and nobody understands how it works. Here is what makes this impossible. Information cannot travel faster than light. This is a fundamental rule of relativity. The speed of light is the universe's speed limit. Nothing exceeds it, but entangled particles communicate instantaneously across any distance. You measure one, and the other responds immediately, not after a delay. Right now, Einstein called this spooky action at a distance. He thought it proved quantum mechanics was incomplete. There must be hidden variables we have not discovered yet. Some deeper reality explaining the connection. In 1964, physicist John Bell proved Einstein was wrong. He formulated an inequality that hidden variable theories must satisfy. Then experiments tested it. Bell's inequality is violated consistently, repeatedly. This is confirmed experimental data. Hidden variables cannot explain entanglement. The particles really do communicate faster than light, or they share information in a way that transcends space and time. Let me give you a concrete example. You create two entangled photons, send one to a laboratory on Earth, send the other to a laboratory on Mars. Measure the polarization of the photon on Earth. The photon on Mars instantly takes the opposite polarization before light from Earth could possibly reach Mars. Before any signal traveling at light speed could cross the distance, the two photons behave as one system, despite being separated by millions of miles, like they are reading the same data file, accessing the same code. This is exactly how variables in computer programs work. Two parts of the code can reference the same memory address. Change one, and the other updates automatically, not because information traveled between them, but because they point to the same location in storage. Entangled particles might work the same way. They are not separate entities communicating across space. They are two access points to the same underlying information. This fits perfectly with holographic universe theory. If all information in our three-dimensional space is actually stored on a two-dimensional boundary, then distance is an illusion. Entangled particles appear far apart in our projected reality, but at the information level, they are right next to each other. Physicist Mark van Ramsdonk has shown that entanglement is essential for space-time to exist. In holographic theories, quantum entanglement between particles creates the geometry of space. Remove entanglement, and space disappears. This is a leading theory in quantum gravity research. Space is not fundamental. It emerges from entanglement patterns in underlying information. Think about what this means for you right now. The atoms in your body are entangled with particles throughout the universe. Your past light cone includes everything that could have influenced you since the Big Bang. You are not a separate, isolated entity. You are a localized pattern in a universal web of quantum connections, and those connections transcend spatial distance. Scientists have tested entanglement at increasingly large scales, entangling photons across hundreds of miles, entangling thousands of atoms simultaneously, even planning experiments to test entanglement between Earth and satellites in orbit. Every test confirms the same thing. Entanglement is real, instant, universal, but the most disturbing application of entanglement is quantum teleportation. This is not science fiction. It is working technology being developed right now. You cannot teleport matter, but you can teleport quantum states. Take a particle here, measure its properties, use entanglement to transfer those exact properties to a particle somewhere else. The original particle is destroyed in the process. The distant particle becomes identical to what the original was. Information traveled, but matter did not. Chinese scientists successfully teleported quantum states to a satellite in orbit. European teams are working on quantum networks spanning entire continents. This only makes sense if information is more fundamental than matter. If particles are not physical objects, but information patterns, and if reality is information, then there is nothing stopping it from being pure mathematics. Which brings us to one of the most radical theories in physics. Max Tegmark is a physicist at MIT. He has proposed something most scientists consider insane. He says the universe is not described by mathematics. It is mathematics. Physical reality and mathematical structure are the same thing. What we experience as matter and energy are actually just equations being computed. This is called the mathematical universe hypothesis, and disturbing amounts of evidence support it. Think about everything we know in physics. Every law, every force, every particle, all of it is described by mathematics perfectly, not approximately, exactly. Newton's laws are equations. Maxwell's equations describe electromagnetism. Einstein's field equations explain gravity. Quantum mechanics is pure mathematical formalism. But here is what Tegmark noticed. We do not just describe nature with math. Nature obeys math without exception. No physical law has ever been found that cannot be expressed mathematically. Why would the universe follow mathematical rules unless it is mathematical? Tegmark's argument goes deeper. He says that if a mathematical structure exists, it has physical existence. Every possible arrangement of numbers, every consistent set of equations, corresponds to a real universe somewhere. This is called the level 4 multiverse. It contains every mathematically possible reality. Our universe is just one solution to one set of equations. Critics call this absurd. They say mathematics is a human invention, a tool we created to describe nature. It does not exist independently. Tegmark disagrees. He points out that mathematical truths are discovered, not invented. The Pythagorean theorem was true before humans existed. Prime numbers existed before we identified them. Math is external to us. It has properties we explore, but do not create. And here is where it connects to simulation theory. If the universe is mathematics, then it is fundamentally computational. Mathematics is computation. Running equations is what computers do. Our universe could be a mathematical structure being computed by some system. The computation generates our experienced reality as output. Physicist John Wheeler proposed a similar idea decades ago. He said information is the foundation of reality, not matter, not energy, information. He coined the phrase it from bit. Everything physical emerges from information processing. But Tegmark goes further. He proposes that only certain mathematical structures exist physically, specifically structures that are computable and decidable in a Gödel sense. This is the computable universe hypothesis. It places an upper limit on complexity. Only mathematical structures, simple enough to be calculated, can become real universes. This would explain why our universe follows relatively simple laws, why physicists keep finding elegant equations, why nature takes computational shortcuts. If the universe were truly arbitrary, its laws could be infinitely complex. Instead, we find symmetries, conservation laws, and principles like least action. All of these are compression techniques, ways to generate maximum complexity from minimum rules. Critics argue that Tegmark's hypothesis is unfalsifiable. How would you test whether the universe is mathematical? Every experiment uses mathematics. Every observation requires mathematical description. Tegmark says the hypothesis makes predictions. It predicts that physics research will continue finding mathematical regularities, that no physical phenomenon will ever be discovered that cannot be modeled mathematically. So far, this prediction, every new discovery in physics, fits into mathematical frameworks. From the Higgs boson to gravitational waves to quantum entanglement, nothing defies mathematics. Some philosophers reject the mathematical universe hypothesis on principle. They say it confuses description with reality. A map is not the territory. The equation describing an electron is not the electron itself. But how do you distinguish between the two? If the electron has no properties other than mathematical ones, then what exactly is the spin, charge, mass? These are all just numbers. Change the numbers and you change the particle. The numbers are the particle. This gets even stranger when you consider quantum mechanics. Particles do not have definite properties until measured. Before measurement, they exist as wave functions, mathematical descriptions of probability. If reality is mathematical before observation creates definiteness, then maybe it is mathematical all the way down. And nowhere is this more obvious than in the fundamental constants themselves. There are no messy physical laws. Every force in nature can be described by an equation, not an approximation, not a rule of thumb, a perfect mathematical relationship. This should not be possible. The universe could have been chaotic, random, following no patterns at all. Instead, it obeys mathematical rules with absolute precision. Take gravity. Isaac Newton wrote down an equation 300 years ago, F = m1, m2, r. This equation works for every massive object in the universe. Drop a ball, orbit a planet, calculate galaxy motion. Same equation. Einstein improved it with general relativity. But general relativity is also pure mathematics. The stress-energy tensor equals 8 pi gc to the fourth, the Einstein tensor. Beautiful, precise, universal. Why does matter curve space-time? according to this exact equation. Why not some other relationship? Why not different rules for different situations? Electromagnetism is equally elegant. Maxwell's four equations describe every electrical and magnetic phenomenon, from lightning to radio waves to the light hitting your eyes right now. Four equations, no exceptions. The strong nuclear force follows equations from quantum chromodynamics. The weak force obeys electroweak theory. Even the newly discovered Higgs field has a precise mathematical description. Nothing in nature resists mathematics. This is deeply suspicious. If the universe is made of physical stuff, why should it care about equations? Matter could do whatever it wants. Instead, it follows rigid mathematical laws. Unless matter is not the foundation, unless mathematics is the foundation, and matter is just one way, the math-physicist Eugene Wigner wrote a famous paper about this. He called it the unreasonable effectiveness of mathematics in the natural sciences. He said, "It is a miracle that math works so well for describing reality. But maybe it is not a miracle. Maybe it is if reality is computation running mathematical structures, then of course every physical law is an equation. The laws are literally lines of code. Symmetry is another clue. Physicists love symmetry because it simplifies equations. If a system is symmetric, you can use that symmetry to reduce the complexity of calculations. But here is what is strange. Nature respects every symmetry physicists discover. Conservation of energy comes from time symmetry. Conservation of momentum comes from space symmetry. Conservation of charge comes from gauge symmetry. These are not coincidences. These are deep connections between mathematics and physics, between abstract principles and concrete reality. Emmy Noether proved in 1915 that every continuous symmetry corresponds to a conservation law. This is Noether's theorem, one of the most profound results in physics. Why should the universe obey Noether's theorem? Why should abstract mathematical relationships dictate physical behavior? Because the universe is mathematics, and it gets more extreme. Quantum field theory describes particles as excitations in fields. But what is a field? It is a mathematical function that assigns a value to every point in spacetime. Nothing physical, just numbers. An electron is a ripple in the electron field. The numbers at that location in the field are higher than baseline. That is all an electron is, a pattern of numbers. This raises an uncomfortable question. If everything is mathematical patterns, what is doing the computing? What system is running these equations? Some physicists say no computer is needed. Mathematical structures exist independently. They do not need to be calculated by anything. They just are, but this seems unsatisfying. In our experience, mathematics requires a mind or a machine to process it. Equations do not solve themselves unless there is something we are missing, some underlying computational substrate that all mathematical structures inhabit, or the universe is self-computing. It processes its own equations in real time, each moment calculating the next moment using physical laws as algorithms. This is the loop theory. Reality emerges from its own computation. There is no external processor. The universe is both the code and the machine running the code. Physicist Stephen Wolfram has proposed a related idea. He says the universe is a cellular automaton, a simple computational system following basic rules. Complex behavior emerges from simple starting conditions. He has shown that very simple cellular automata can generate incredibly complex patterns. Patterns that look like physics, like spacetime, like quantum mechanics. If Wolfram is right, the entire universe could be running on rules as simple as a few lines of code. And maybe that code has fingerprints, signatures that reveal its digital nature. What if spacetime has pixels? This is the central question of digital physics. It proposes that the universe is not infinitely smooth. Instead, it is discrete, made of tiny indivisible units like a computer screen. From a distance, it looks continuous. Up close, you see individual pixels. The resolution is finite. Several theories in physics point toward this. Quantum mechanics already assumes discrete energy levels. Electrons orbit atoms at specific distances, not in between. They jump from one orbit to another without passing through the space between. This is quantization. Reality comes in chunks. But digital physics goes further. It suggests space itself is quantized. There is a smallest possible distance called the Planck length, about 10⁻⁵ millimeters. Below this scale, the concept of distance breaks down. Space-time becomes grainy, foamy, discrete. This is not proven, but multiple approaches to quantum gravity predict it. String theory, loop quantum gravity, causal set theory, all of them require space-time to be fundamentally discrete at the smallest scales. If true, this means the universe has a resolution limit. Like a video game engine, the smallest unit of space is 1 Planck length. The smallest unit of time is 1 Planck time, about 10⁻⁴ seconds. Nothing can be smaller than this. Reality is pixelated. Physicist Konrad Zuse proposed in 1969 that the universe is a digital computer. He suggested it runs on cellular automaton rules, processing reality one step at a time. Nobody took him seriously at the time. Now the idea is mainstream. Digital physics faces challenges. Most physical theories assume continuous symmetries. Rotational symmetry means the laws of physics are the same regardless of orientation. Translational symmetry means they are the same at every location. But a pixelated universe breaks these symmetries. If space is a grid, there are preferred directions. Horizontal and vertical would be different from diagonal. We observe no such preference. The universe appears perfectly symmetric. Symmetry? Particles moving at different speeds, depending on direction. Experiments advocates of digital physics respond that the pixel size is so small, we cannot detect asymmetries yet. But at high enough energies, we should see violations of Lorentz arching for these violations now. Ultra-high energy cosmic rays, particles from space hitting Earth with enormous energy. If space-time is discrete, these particles should show directional preferences. So far, no violations have been found, but the search continues. Another prediction of digital physics involves information limits. If the universe is computational, it has finite processing power. This means there is a maximum amount of information that can exist in any region. This is already suggested by black hole thermodynamics. The amount of information in a black hole is proportional to its surface area, not its volume, a two-dimensional limit on three-dimensional space. Exactly what you would expect from a holographic simulation running on finite hardware. Some scientists have proposed tests. If the universe is digital, certain quantum effects should behave differently. Particles should decohere faster in systems near the information limit. Gravitational wave detectors might be sensitive enough to detect granularity in spacetime. If space has pixels, gravitational waves should show tiny irregularities, a kind of static. The GEO 600 detector in Germany has detected unusual noise patterns. Some researchers interpret this as evidence of holographic noise, the grainy texture of reality showing through. This interpretation is controversial and not widely accepted, but it is being studied seriously. Stephen Wolfram has been developing his physics project, an attempt to derive all of physics from simple computational rules. He has published models that generate relativity and quantum mechanics from networks of discrete elements. His approach treats space as a graph, points connected by edges. The rules determine how connections change over time. From these simple rules, space-time geometry emerges. He claims his models produce particles, forces, and even hints of quantum mechanics. Critics say the models are too flexible. You can make them produce almost anything by adjusting the rules, but the core idea remains intriguing. What if reality is computation all the way down? What if the universe is software running on hardware we cannot see? And what if we found direct evidence of the simulation, something that should not exist in an organic, natural universe? That evidence might already be here. In Germany, there is a machine built to detect the faintest vibrations in spacetime. It is called the GEO 600 gravitational wave detector. It is so sensitive, it can measure distortions smaller than the width of an atomic nucleus. Scientists use it to observe black holes colliding billions of light years away, but they found something else, something nobody expected. Not ordinary noise from mechanical vibrations or electrical interference, a specific pattern, a grainy static that should not be there. Like the universe itself is pixelated, and the detector is sensitive enough to see the pixels. Craig Hogan at the Fermilab Particle Physics Laboratory studied these signals. He proposed that this could be holographic noise, the fundamental graininess of spacetime, showing up in measurement. Here is how it works. If the universe is a holographic projection from a two-dimensional surface, then information has limits. The Planck scale sets the minimum resolution. Below that, space and time become uncertain. This uncertainty would appear as random fluctuations, like static on an old television. Gravitational wave detectors are precise enough to potentially see these fluctuations. The GEO 600 detected unexpected noise in exactly the frequency range holographic models predict. Not everywhere, not random, in specific patterns matching theoretical predictions. This is controversial. Many scientists argue the noise has mundane explanations: seismic activity, temperature fluctuations, laser instability. The detector is incredibly sensitive. Many things could cause spurious signals, but Hogan and his colleagues ruled out conventional sources. They analyzed the data carefully. The noise persists even after accounting for known interference. If this is holographic noise, it means we are seeing the resolution limit of reality. The universe is not infinitely smooth. It has a grain structure, like zooming into a photograph until you see individual pixels. Other experiments are testing this idea. The holometer at Fermilab was specifically designed to detect holographic noise. It uses laser interferometry to measure spacetime fluctuations at the Planck scale. Initial results were inconclusive. The detector did not find the specific signature researchers expected, but this does not disprove holographic noise. It only rules out certain models. The search continues with more sensitive instruments. LOGI, the Laser Interferometer Gravitational Wave Observatory, has also looked for anomalies. So far, nothing definitive. But here is what makes this so important. If holographic noise exists, it proves spacetime is not fundamental. Space and time are emergent properties of underlying information. Reality is discrete, and discreteness is the signature of computation. Every computer operates on discrete values. Bits, ones and zeros, continuous values must be approximated using finite precision. This creates rounding errors, tiny discrepancies that accumulate over many calculations. If the universe is a simulation, it would show similar artifacts, places where the approximation breaks down, where the discrete nature of the computation becomes visible. Scientists have proposed looking for these artifacts in cosmic rays, high-energy particles from space. If spacetime is pixelated, particles moving near the speed of light should show directional preferences. Certain angles would be slightly favored over others. This has not been observed yet, but the energy range tested so far may not be high enough. Ultra-high energy cosmic rays, the most energetic particles ever detected, are rare. More data is needed. Another place to look is the cosmic microwave background, the afterglow of the Big Bang. It shows temperature variations across the sky. These variations contain information about the early universe. Some patterns in this data are unexpected anomalies that do not fit standard cosmological models perfectly. Cold spots, alignments, statistical irregularities. Most cosmologists think these are just random fluctuations. Nothing special, but a few researchers argue they could be signatures of underlying computational structure. If the universe runs on a grid, there should be preferred directions in space. The cosmic microwave background might reveal these preferences as subtle asymmetries. Studies have found hints, nothing definitive, nothing that cannot be explained by chance, but enough to keep the question open. The truth is, we do not yet have the technology to definitively test whether spacetime is discrete. Our instruments are close, within perhaps 1 or 2 orders of magnitude of the sensitivity needed. In the next decade, new detectors will come online, more sensitive gravitational wave observatories, better cosmic ray telescopes, improved measurements of the cosmic microwave background. If holographic noise is real, we will find it soon. And if we do, everything changes. The cosmic microwave background is the oldest light in the universe. It comes from 380,000 years after the Big Bang. Before that, the universe was too hot for light to travel freely. Then it cooled enough for atoms to form and photons to escape. Those photons have been traveling through space ever since. We detect them as microwave radiation coming from every direction. This glow tells us what the early universe looked like, and it contains patterns that should not exist. The temperature varies slightly across the sky. Tiny fluctuations. These fluctuations are the seeds of all structure in the universe. Regions that were slightly denser became galaxies, slightly less dense became voids. Standard cosmology predicts these fluctuations should be random, following a specific statistical distribution called a Gaussian random field. And mostly they do, but not everywhere, not completely. In 2017, a team of scientists published evidence supporting a holographic universe. They analyzed irregularities in the cosmic microwave background using holographic models. The results matched holographic predictions, as well as they matched standard inflation models. This does not prove the universe is holographic, but it shows holographic models are equally valid explanations for what we observe. There are other anomalies. The cold spot, a region of the sky where the cosmic microwave background is significantly colder than expected, about 0.007 degrees C below average, spanning roughly 5 degrees across the sky. This should be extremely unlikely. Random chance predicts features this large and cold should appear only once in thousands of universes. Yet here it is. Some researchers proposed it could be a supervoid, a massive empty region between us and the cosmic microwave background. Hitting traveling through the void would lose energy and appear colder. But surveys of galaxies do not show a void large enough. The explanation does not work. Another theory suggests the cold spot could be evidence of a collision with another universe, a bubble universe bumping into ours. This is pure speculation, but mathematically possible in multiverse models. Or it could be a computational artifact, a glitch in the simulation, an error that propagated through the calculations and left a signature in the data. There are more anomalies. The axis of evil, a name cosmologists gave to an unexpected alignment in the cosmic microwave background. Large-scale temperature patterns seem to line up with the plane of the solar system. This should be impossible. The cosmic microwave background comes from the edge of the observable universe. Events here should have no correlation with patterns there. The two are causally disconnected. Light has not had time to travel between them since the Big Bang. Yet the alignment exists. Multiple studies have confirmed it. Nobody knows why. Some scientists dismiss it as coincidence. Others say it reveals problems with our cosmological models, and a few suggest it indicates something fundamentally wrong with our understanding of space and time. If the universe is a simulation, preferred directions could emerge from the coordinate system used in the code, like how video game environments often use Cartesian grids aligned with the screen. The programmer's choice of coordinates could leave traces in the output, subtle but detectable. Roger Penrose has also pointed to anomalies. He argues the cosmic microwave background shows more uniformity than inflation predicts. The universe is too smooth on large scales. This suggests something other than inflation shaped the early universe. Penrose proposes conformal cyclic cosmology, the idea that our Big Bang was the end of a previous universe. But this is also speculative and lacks strong evidence. What we know for certain is the cosmic microwave background contains surprises, features that do not fit perfectly into standard models. Most are probably just statistical flukes, unusual but not impossible. But some patterns persist. The cold spot has not gone away. The axis of evil remains aligned. These are confirmed observations that need explanation. And as our measurements improve, we keep finding more irregularities, smaller anomalies, deviations from perfect randomness. Each one could be nothing. Altogether, they could be pointing towards something profound, a message hidden in the oldest light we can see. If that message exists, we are only beginning to decode it. A philosopher at Oxford University proved something disturbing. Not that we live in a simulation, but that at least one of three statements must be true. His name is Nick Bostrom. In 2003, he published a paper that changed how scientists think about reality. The argument is airtight, pure logic. You cannot escape its conclusions. Here are the three possibilities. At least one must be true. First, civilizations go extinct before developing the technology to run realistic simulation. Something kills every advanced species before they reach that point. War, climate disaster, artificial intelligence gone wrong. Whatever the cause, nobody survives long enough to build ancestor simulations. Second, advanced civilizations develop the technology but choose not to use it. Either they decide simulating conscious beings is unethical, or they lose interest, or they are prevented by laws. For some reason, nobody runs these simulations even though they could. Third, we are almost certainly living in a simulation right now. Bostrom proves these are the only options, and he shows that if the first two are false, the third must be overwhelmingly probable. Here is the logic. Assume civilizations sometimes survive to become technologically advanced. Assume some of them run ancestor simulations, programs that recreate their evolutionary history, simulations detailed enough that the beings inside are conscious. How many simulations would they run? Millions? Billions? A single advanced civilization could run countless simulations using a tiny fraction of the computational resources available in their galaxy. Each simulation would contain billions of conscious beings living out simulated lives. Now do the math. How many real civilizations exist? Maybe thousands across the observable universe. How many simulated civilizations? Trillions? Quadrillions? The simulated beings vastly outnumber the real ones. If you are a conscious being, what is more likely? That you are one of the rare real ones, or one of the numerous simulated ones? The odds favor simulation by an enormous margin. Bostrom is careful to say this does not prove we are in a simulation. It only shows that if simulations are possible, and sometimes created, then most conscious beings are simulated. But it raises the probability dramatically from something you might dismiss as science fiction to something you should take seriously. Elon Musk has cited this argument. He says, the odds we are in base reality are 1 in billions. His reasoning is simple. Video games already create believable virtual worlds. They improve exponentially. In a few decades, we will have simulations indistinguishable from reality. If we can do this, other civilizations can too. And they probably already have. Many times over, we could be characters in someone else's game. Some philosophers object to the simulation argument. They say it assumes too much. Maybe advanced civilizations cannot run conscious simulations. Maybe consciousness requires biological substrates. Maybe the computational requirements are fundamentally impossible. But Bostrom only needs the possibility to be non-size. As long as some civilizations run simulations, the logic follows. Simulated beings will outnumber real ones. Others argue the simulation hypothesis is unfalsifiable. How would you test it? Any evidence you find exists within the simulation. The simulators could fake anything. This is true, but does not make the argument invalid. Some true statements cannot be directly tested. That does not mean they are false. What makes Bostrom's argument powerful is its structure. It is a trilemma, 3 options. One must be true. You can argue about which one, but you cannot dismiss all 3. Either we are doomed to extinction, or advanced civilizations universally choose not to simulate, or we are in a simulation. Personally, I find the first 2 options less plausible than the third. Civilizations probably sometimes survive, and if simulation technology exists, someone will use it. Curiosity alone drives that, which leaves the uncomfortable conclusion we are probably simulated, and if we are, there might be ways to detect it. Not by finding the simulators, but by finding glitches, limits, places where the simulation cuts corners. Scientists are already looking. Elon Musk does not say things lightly. He calculates, he analyzes, and when he speaks about the nature of reality, people listen. At a conference in 2016, Musk made a statement that rippled through the technology and science communities. He said, the odds that we are living in base reality are 1 in billions. Not metaphorically, he means it literally. The probability that this is real, not simulated, is effectively zero. His reasoning comes from the pace of technological advancement. 40 years ago, video games were Pong, two rectangles, and a dot. Now we have photorealistic virtual worlds, characters with complex behaviors, physics engines that simulate reality convincingly. This improvement happened in 4 decades, a blink in cosmic time. Extrapolate forward. In another 40 years, games will be indistinguishable from reality. Full immersion virtual worlds, conscious artificial intelligences, simulations that feel completely real to everyone inside them. Now extend that timeline. Not 40 years, not 100, thousands of years, millions of years. What could a civilization a million years more advanced than us create? Simulations perfect in every detail. Universes as complex as ours. Conscious beings who have no idea they are simulated. And here is the key point. If one advanced civilization creates simulations, they create many. Why run one when you can run millions? Each simulation could contain billions of conscious beings, so count the conscious minds in existence. A few billion humans in base reality, trillions of simulated humans across millions of simulations. The simulated minds outnumber real minds by factors of millions or billions. You are conscious. What are the odds you are one of the rare base reality minds versus one of the numerous simulated ones? Billions to one in favor of simulation. Musk also points out that progress toward realistic simulation is inevitable, unless something stops it. Extinction, technological plateau, deliberate choice to stop, but extinction seems unlikely for all civilizations. Some will survive. Technological plateau contradicts every trend we observe. Technology accelerates, and choosing not to simulate seems implausible when curiosity is universal. Therefore, simulations will be created, are being created, have been created countless times already. Other tech leaders agree. Many in Silicon Valley take simulation theory seriously, not as philosophy, as probability. Some go further and suggest we might detect the simulation. If our universe is running on finite computational resources, there should be limits, optimizations, shortcuts. Musk himself has joked that we should hope we never make the simulation too boring, or the simulators might shut it down. Accelerating technological progress keeps things interesting, gives them reason to keep the program running. This raises ethical questions. If we are simulated, do our experiences matter? Are our lives real? Musk would say yes. Consciousness is real, regardless of substrate. Simulated suffering, simulated joy is still joy. The medium does not matter, the experience does. Connects to his work on artificial intelligence. If consciousness can exist in silicon as well as carbon, then there is no fundamental difference between biological and artificial minds. Both are information processing systems. And if consciousness is substrate independent, then simulated beings are as real as base reality beings. Their lives have equal value. But this also means we have responsibilities. If we develop simulation technology, we become simulators, creating conscious beings in virtual worlds. Those beings would depend on us for their existence. Shutting down the simulation would be murder. Manipulating it would be tyranny. Musk believes we are already on this path. Neural interfaces, brain-computer connections, virtual reality, artificial intelligence, all of these push toward the ability to create conscious simulations. Within this century, we might run ancestor simulations ourselves, creating virtual worlds populated by conscious AIs, experiencing simulated histories. And when we do, we will understand our own situation better, because we will be simulators looking at our simulations, just as our simulators might be looking at us. The hierarchy could extend indefinitely, simulations within simulations, each level creating the next reality as nested computation. This is not provable yet, but Musk finds it more plausible than the alternative, that we just happen to exist at the exact moment in history, before simulation technology is perfected, that we are the base reality, the original. The odds are simply too little. To accept what the mathematics implies, we are probably simulated, and if we are not, we will become simulators soon. Either way, the question of what is real becomes much more complicated. There is a specific type of simulation that advanced civilizations would want to run. Not games, not experiments, history. They would simulate their own past, watch their species evolve, see how their ancestors lived, study pivotal moments, run alternative scenarios. These are called ancestor simulations. Nick Bostrom proposed them as the most likely type of simulation for advanced civilizations to create. Here is why they matter. If ancestor simulations are common, then most conscious beings throughout the universe are living in recreations of their species' history, not in the base timeline, but in one of countless reruns. Think about what this means for us. Humans are interesting. We are at a critical point. Climate change, artificial intelligence, nuclear weapons, genetic engineering, the decisions we make now will determine our species' future. This is exactly the period an advanced human civilization would want to study. They would run millions of simulations of early 21st century Earth, testing different variables, seeing which choices lead to survival and which to extinction. We could be in one of those simulations right now, a detailed recreation of Earth between 2000 and 2100, billions of simulated humans living simulated lives, unaware they are being studied. The simulators would have records. They know how history actually went, but they want to explore variations. What if a pandemic is handled differently? What if a war does not happen? What if technology develops faster or slower? Each simulation tweaks variables slightly, then watches what emerges. From inside the simulation, everything feels real. We have memories, families, goals, pain, and pleasure. Our experiences are genuine, even if our substrate is not. And here is something disturbing. The simulators might run the same period many times, resetting and trying again. You could have lived this year before many times with slight variations, but your memories reset each time. You have no way to know. This is the problem of Boltzmann brains applied to simulations. In an infinite multiverse, you are more likely to be a random fluctuation than an ordered observer. In infinite simulations, you are more likely to be in a short-running test than a complete historical recreation. Unless simulators prefer running complete histories, then most simulated beings live full lives from birth to death without resets. We have no way to know which scenario applies. Some philosophers argue ancestor simulations would be unethical. Creating billions of conscious beings just to study them is morally questionable, especially if those beings suffer wars, disease, natural disasters, all the horrors of history. Would an enlightened civilization inflict that on simulated people? Maybe yes, if the knowledge gained justifies it. Understanding how civilizations survive existential risks could save countless real lives. The suffering of simulated beings might be an acceptable cost. Or maybe the simulators believe simulated suffering is not real suffering, that only base reality experiences matter. This seems wrong, but we cannot rule it out. Another possibility is that ancestor simulations sanitize the worst part. They run relatively peaceful periods, or they skip over traumatic events, creating an idealized version of history rather than a faithful recreation. If true, we should expect our world to be less terrible than random chance would predict. Maybe we are in a curated simulation, one where existential catastrophes are turned down in intensity. This is unfalsifiable speculation, but it is interesting to consider. What we can say is this: if ancestor simulations exist, we are probably in one. The numbers demand it. Real historical periods happen once, simulated ones happen millions of times. Being in the original timeline would make us incredibly special, uniquely privileged. The odds are against it. Better to assume we are one simulation among many, not the prime reality, but a copy being studied by future versions of ourselves. And if that is true, it changes how we should think about our choices. Maybe the simulators are watching specifically to see how we handle artificial intelligence or climate change or biotechnology. Our decisions might teach them what to avoid in their own timeline. Or maybe this is all wrong. Maybe simulations are impossible. Maybe consciousness requires something that cannot be reproduced computationally. But every year, artificial intelligence gets more sophisticated. Every year, virtual worlds get more realistic. The trend points towards simulation being possible, and if possible, then probable, and if probable, then we are likely already there. Nature is lazy in the most precise mathematical sense. The universe always takes the easiest path. This is called the principle of least action. It says that particles moving through space follow trajectories that minimize a quantity called action, not distance, not time, but action. Action is the integral of kinetic energy minus potential energy over time. This is a specific mathematical quantity, and nature minimizes it perfectly every single time. Light takes the path of least time through space. A ball thrown through the air follows the trajectory of least action. Planets orbit in paths that minimize action. No exceptions. But here is the question: why would the universe care about minimizing anything? Physical objects are not conscious. They do not calculate optimal paths. They just move. Yet somehow they always find the minimum action solution, like they are solving an optimization problem in real time. This is exactly how computer simulations work. To predict where a particle will be in the future, you solve an optimization problem, find the path that minimizes action. That path is where the particle goes. The universe behaves like a computer running physics calculations. It finds optimal solutions using the same methods programmers use. Fermat's principle describes this for light. Light traveling through different materials bends at interfaces, water to air, air to glass. The angle of bending follows a precise law. Snell's law gives the formula. But Fermat explained why. Light takes the path that gets from point A to point B in the least time. It automatically solves an optimization problem that would take humans significant calculation. This happens because light explores all paths simultaneously as a quantum superposition, then interferes with itself. The path of least time constructively interferes. All other paths cancel out. But this is computational. The light is effectively calculating which path is optimal by trying all of them and selecting the result. Quantum mechanics is full of these shortcuts. The path integral formulation sums over all possible histories a particle could take, then assigns probabilities based on which histories interfere constructively. This is an elegant computational trick. Instead of tracking one definite path, calculate contributions from every possible path. Let the math determine the outcome. Physicist Richard Feynman developed this formulation. He showed it produces identical predictions to standard quantum mechanics, but reveals something deeper about how nature works. The universe is not evolving one state forward in time. It is summing over all possibilities and selecting outcomes based on interference patterns. This is Monte Carlo simulation, a computational technique used in weather prediction, finance, nuclear physics, and computer graphics. You cannot calculate the exact answer, so you sample many possibilities and average the results. Nature does this natively. Conservation laws are another computational shortcut. Energy is conserved. Momentum is conserved. Charge is conserved. These laws dramatically reduce the complexity of calculations. Without conservation laws, you would need to track every particle individually, calculate forces, update positions, check for interactions. Computationally expensive. With conservation laws, you know the total energy at the end equals the total at the start. This constrains possibilities, reduces computation. Symmetries are even more powerful. If a system has rotational symmetry, you can ignore orientation. If it has time symmetry, the laws do not change over time. Each symmetry eliminates variables. Know proved that every symmetry corresponds to a conservation. This is not coincidental. Symmetries are computational optimizations. Nature uses them to reduce processing requirements. The speed of light acts as a frame rate cap. Nothing moves faster than light. This limits how quickly information can propagate in a simulation. This prevents errors from accumulating. Events outside your light cone cannot affect you yet. This is how distributed computing works. Separate parts of the system update independently until signals reach them. The speed of light enforces causal structure, keeps the simulation consistent. Some physicists have noticed quantum mechanics itself might be a compression algorithm. The wave function contains less information than a complete classical description would require, yet it generates all observable predictions. This is suspicious. Why would nature use a reduced description unless computational resources are limited? Quantum entanglement lets particles share information without storing it separately. Two entangled particles are described by one wave function, not two independent ones. This halves the memory requirement. If the universe is maximizing efficiency, these patterns make sense. Every shortcut, every symmetry, every conservation law reduces the computational load, and the reduction is enormous. Without these efficiencies, simulating even a small region of space would be impossible. With them, reality becomes computable. The speed of light is 299,792,458 miles/s, not approximately, exactly. This value is defined. Nothing moves faster, not matter, not energy, not information. This is the universe's absolute speed limit. But why does this limit exist? What enforces it? Einstein showed that the speed of light emerges from the structure of spacetime. Space and time are not separate. They are dimensions of a four-dimensional continuum. Moving through space means moving through time. The speed of light is the conversion factor, but this still does not explain why that particular conversion factor. Why not faster? Why not infinite? One answer comes from simulation theory. The speed of light acts like a frame rate cap. It limits how quickly information can propagate through the system. In a computer simulation, you cannot process everything instantaneously. The program updates in steps. Each step, the computer calculates new positions based on forces and velocities, then displays the result. If objects could move arbitrarily fast, the simulation would break. Particles would teleport across the universe before the next frame. Causality would become impossible to maintain. So you set a maximum speed. Nothing moves more than a certain distance per time step. This keeps the simulation stable, prevents information from jumping ahead. The speed of light could be exactly that, a maximum propagation speed set by the simulation's time step and spatial resolution. Calculate the numbers. The Planck length is about 10^35 millitem. The Planck time is about 10^44 seconds. Divide them and you get roughly the speed of light. These are not coincidental relationships. The Planck length and Planck time are the minimum units of space and time. The speed of light connects them. This is exactly what you would expect if space-time is a discrete grid. Each time step, information moves one spatial unit. The ratio is the speed of light. But there is more. The speed of light also limits causality. Events outside your light cone cannot affect you yet. You only need to process interactions within your local region. This dramatically reduces computational complexity. Instead of calculating every particle in the universe influencing every other particle, you only calculate local interactions. Distant objects become relevant only when their light reaches you. This is called the light cone structure of space-time. It is fundamental to relativity, but it is also a brilliant optimization strategy. In massively multiplayer online games, servers use similar tricks. Your client only receives updates about nearby players. Distant players are abstracted, maybe shown as icons on a map, but not fully rendered. This keeps the bandwidth manageable. The server cannot send complete information about every player to every other player, so it restricts updates to local regions. The speed of light does the same for the universe. It partitions reality into regions that can be processed independently, then integrates them as information arrives. Quantum mechanics adds another layer. The uncertainty principle prevents you from knowing both position and momentum precisely. This limits the information content of the universe. If you could know everything about every particle, the simulation would need infinite memory, but uncertainty caps the information. Each particle has finite information content. This makes the simulation possible. The speed of light also explains why time dilation occurs. Moving clocks run slow. This should not happen if time is absolute, but if time is part of the simulation's processing, then moving through space means spending fewer updates on time progression. You have a fixed computational budget per particle, Spend more on spatial motion, and you have less for temporal progression. Time slows down. This is exactly how time dilation works in relativity, and it is exactly how you would implement time in a simulation with limited resources. Energy also obeys a speed limit. EEMC curve. Mass is energy divided by the speed of light squared. This formula connects energy, mass, and the speed of light. Why would they be related? In simulation terms, mass is information. Energy is the cost of changing that information. The speed of light sets the exchange rate. More massive objects require more computation to update. Accelerating them requires more energy. The speed of light determines how much. Some researchers have proposed testing whether the speed of light is truly constant. If spacetime is discrete, light speed might vary slightly depending on direction, aligned with the grid versus diagonal. So far, no variation has been found, but experiments continue improving. Field measurements might detect tiny anisotropies. If they do, it would strongly suggest spacetime is computational. A grid with preferred directions. Even if they do not, the speed of light still looks suspicious, too convenient, too perfectly suited to making the universe computable, like someone designed it that way. We arrive at the hardest question in all of science. What is conscious, and why does it seem to change reality when it observes? The double-slit experiment shows that observation collapses the wave function. Before measurement, particles exist in superposition. After measurement, they become definite. But what counts as measurement? Does it require consciousness? Some interpretations of quantum mechanics say yes. The wave function collapses only when a conscious observer becomes aware of the result. Until then, the particle remains in superposition. This is called the consciousness causes collapse interpretation. It was popular among early quantum physicists. Eugene Wigner advocated for it. John von Neumann explored it mathematically, but most modern physicists reject this view. They argue that any interaction with the environment causes decoherence. Consciousness is not special. A detector, a photon, even an air molecule can collapse the wave function. This is the mainstream position, and it is probably correct, but it does not explain why observation matters at all. Why does measuring a particle force it into a definite state? What makes observation different from any other interaction? The answer might be information. Observation creates a permanent record. Before observation, the particle's state is uncertain, ambiguous. After observation, information exists about which state it is in. This information cannot be erased. It becomes part of the universe's history. And once information exists, the particle must be consistent with it. In simulation terms, unobserved particles do not need to be fully rendered. They can exist as probability distributions, potential states that have not been calculated yet. Only when observation occurs does the simulation need to commit to a specific value. At that moment, it runs the calculation, picks a result based on the probability distribution, and updates the simulation state. This is lazy evaluation, a programming technique where calculations are delayed until the result is actually needed. Very efficient for large systems. The universe might work the same way. Most of reality is not being observed at any given moment. Why fully calculate store probability distributions instead? Compute specifics only when required. Consciousness becomes relevant because conscious observers create permanent records. Your brain stores memories. Those memories contain information about what you observe. That information cannot be made consistent with the particle being in a different state. So the wave function collapses. The particle becomes definite. The simulation updates. But this raises a troubling question. If consciousness is what forces reality to become definite, then what existed before consciousness evolved? Did the universe exist in superposition for billions of years? Did the first conscious beings retroactively collapse the wave function of the entire part? This is called the Wigner's friend paradox, extended to cosmic scales. It seems absurd, but some interpretations of quantum mechanics actually suggest this. John Wheeler proposed the participatory universe, the idea that observers do not just measure reality, they participate in creating it. The universe is not a film we watch. It is a play we star in. This sounds mystical, but Wheeler was a serious physicist. He thought quantum mechanics implied something profound about the relationship between mind and matter. If he is right, consciousness might be fundamental, not emergent from matter, fundamental like space and time. This connects to panpsychism, the philosophical view that consciousness is a basic property of the universe, not just in humans and animals, but in everything. Electrons have rudimentary awareness. Protons have experience. Most scientists dismiss this as nonsense, but a few take it seriously. Physicist Roger Penrose has proposed that consciousness arises from quantum processes in neurons, specifically quantum collapses in microtubules. His theory is controversial and lacks strong evidence, but it suggests consciousness might be tied to quantum mechanics at a fundamental level. If simulation theory is correct, consciousness might be the user interface, the way information from the simulation is presented to observers within it. Your brain is not generating consciousness, it is receiving it, like a monitor displaying output from a computer. The computation happens elsewhere. Your brain, it renders the result. This would explain why consciousness feels unified, why you experience a single coherent reality rather than disconnected sensory data. The simulation presents an integrated interface. It would also explain qualia, the subjective experience of redness, the feeling of pain. These are not physical properties. They are how information is presented to consciousness. In a simulation, the code does not need to experience anything, but the user does. So the simulation includes a consciousness interface that converts data into experience. We might be characters in a game, and consciousness is what makes the game playable. This is highly speculative, but it offers an explanation for why consciousness exists and why it seems connected to quantum mechanics. And it suggests that the hard problem of consciousness might be solved by looking outside physical reality. Quantum mechanics is the most successful theory in physics. It predicts experimental results with stunning accuracy, 14 decimal places in some cases. No other theory comes close. Yet nobody knows what it means. This is the measurement problem. Quantum mechanics tells us how to calculate probabilities. It does not tell us what happens during measurement. Why does the wave function collapse? What determines which outcome occurs? The equations are silent. Before measurement, a particle is described by a wave function. This gives the probability of finding the particle in different states. 50% chance here, 30% there, 20% somewhere else. But when you measure, you get one definite result. The wave function collapses to a single state. The probabilities vanish. What causes this collapse? The equations do not say, they describe how the wave function evolves smoothly over time. Then suddenly it jumps discontinuously to one outcome. This is the measurement problem, and after nearly a century, physicists still do not agree on the answer. The Copenhagen interpretation says measurement is fundamental, it just happens. Do not ask why. Calculate the probabilities and move on. This is pragmatic but unsatisfying. It treats measurement as a black box, something outside the equations, which means quantum mechanics is incomplete. The many worlds interpretation eliminates collapse. It says the wave function never collapses. Instead, all possible outcomes occur. The universe splits into branches. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes are real. You just become different versions of yourself in different branches. This solves the measurement problem. By denying measurement is special, nothing discontinuous happens. The wave function evolves smoothly. It just becomes more complex. But many worlds has problems. It requires infinite universes constantly branching. We can never observe other branches, so it is unfalsifiable. De Broglie-Bohm theory adds hidden variables. Particles have definite positions and velocities at all times. We just cannot measure them precisely. The wave function guides the particles but does not represent probabilities. This restores realism. Particles are always somewhere specific, but it requires non-locality. Particles instantly affect each other across space, and the hidden variables are undetectable by definition. Objective collapse theories modify the Schrödinger equation. They add terms that cause spontaneous collapse, usually when systems exceed a certain size or mass threshold. This makes collapse physical, not dependent on observers. Large objects automatically have definite properties. Small objects stay in superposition, but nobody knows what mechanism causes collapse, and experiments have not confirmed the predictions of these theories. Each interpretation has advantages and disadvantages. None are obviously correct. Physicists choose based on philosophical preference. But here is what troubles everyone. The measurement problem should not exist. If quantum mechanics is complete, measurement should be just another physical process described by the same equations. It is not. Measurement is special. It follows different rules. This suggests something is missing, either from our equations or from our understanding of what observation means. Simulation theory offers a possible answer. Measurement is when the simulation commits to a specific value. Before measurement, the system exists as a probability distribution in memory. After measurement, it becomes a definite state. This is exactly how Monte Carlo simulations work. You sample from probability distributions only when you need specific values. Otherwise, you track distributions. If our universe is simulated this way, measurement becomes the moment when sampling occurs. The wave function is the distribution. Collapse is the selection of one sample. This does not prove simulation theory, but it explains why measurement is special, why it follows different rules, because it is a different operation in the code. Upload a quantum state to memory versus sample from it. Two different functions, both necessary but distinct. The measurement problem has stalled progress in physics for decades. We cannot build a quantum theory of gravity, partly because we do not understand what measurement means. If simulation theory is correct, it might provide the missing insight, not by changing quantum mechanics, but by revealing what the equations actually describe. Not ultimate reality, but the output of a computational process. And outputs depend on how you observe them. Scientists are not just speculating about simulation theory, they are testing it right now with real experiments. The question is how. If we are in a simulation, any test we run is also simulated. The results are part of the program. How do you detect a simulation from inside? You look for glitches, limits, places where the simulation cuts corners or makes mistakes. Any sufficiently complex program has bugs. If we find the bugs, we find evidence of simulation. Physicist Silas Bean at the University of Washington proposed a specific test in 2012. He suggested looking at the highest energy cosmic rays particles from space with extreme energies. If space-time is a discrete lattice like a computational grid, then there should be a maximum energy. Beyond that energy, particles would probe distances smaller than the grid space. The simulation would break down. We have not observed such a cutoff yet, but cosmic ray detectors keep improving. If the cutoff exists, we might find it soon. Another test involves correlation patterns. In 2022, physicist Melvin Vopson proposed measuring information content in matter. If his second law of interdynamics is correct, information entropy should decrease in organized systems. This could be tested by measuring the information content of particles before and after they interact. If information consistently decreases, it suggests optimization data compression. Some experiments have looked for quantization of time. If time is discrete, clocks should show tiny irregularities, especially precise atomic clocks. So far, nothing has been found, but the resolution is improved. Next-generation atomic clocks might be sensitive enough to detect Planck-scale time quantization if it exists. Gravitational wave detectors offer another avenue. The GEO 600 found anomalous noise. Other detectors are now searching for similar patterns. If holographic noise is real, multiple independent detectors should see it. LIGO upgraded recently. The sensitivity is now high enough to potentially detect signals from the very early universe. If the Big Bang itself was a computational event, there might be signatures in gravitational waves. Quantum computers provide an interesting possibility. If the universe is quantum computational, then quantum computers might be able to exploit the same shortcuts nature uses. Some researchers are looking for fundamental limits in quantum computation, places where the math says one thing, but experiments show another. These discrepancies could reveal underlying computational architecture. The cosmic microwave background is being mapped with increasing precision. The Planck satellite measured temperature variations to a millionth of a degree. Future missions will improve this further. If simulation theory is correct, there might be patterns we have not noticed yet. Symmetries, alignments, structures that do not fit natural explanations. Machine learning algorithms are now analyzing cosmic microwave background data, looking for anomalies human researchers might miss, patterns that only become visible when you analyze millions of data points simultaneously. Some theoretical physicists are working on prediction. If we are in a simulation, what should we expect to observe? What would distinguish simulated reality from base reality? This is hard because we have only one universe to study. No control group, no comparison, but mathematical models can explore possibilities. One prediction is simplicity. Simulated universes should have elegant laws, efficient algorithms. This matches what we observe. Physical laws are remarkably simple given the complexity they produce. Another prediction is anthropic selection. We should find ours in a universe that just barely allows observers, not optimized for life, but not hostile either. This also matches observations. A third prediction is cosmological coincidences, fine-tuned constants, initial conditions that seem designed, the universe beginning at the exact moment complexity becomes possible. All of these are consistent with simulation, but they are also consistent with multiverse theory, or designed by a deity or unknown physical laws. The challenge is finding a test that distinguishes between these possibilities, a prediction unique to simulation theory. Some researchers propose looking for Easter eggs, jokes programmers hide in code. Maybe the simulators left clues deliberately, mathematical constants that encode messages, patterns in prime numbers, signatures in physical laws. This sounds absurd, but if the simulation is ancestor research, the simulators might want to reveal themselves eventually. They are studying us. Maybe they want us to know. No credible evidence has emerged yet, but the search continues, and the more we look, the more questions arise. Let us assume for a moment that we are right, that every piece of evidence points correctly, that the universe is a hologram, a simulation, a computation running on hardware we cannot see. What changes? First, death might not be final. If you are information in a simulation, that information can be copied, backed up, restored. The simulators could run you again in a different context, a different world. You might have lived before. You might live again. The specific arrangement of atoms in your body is temporary, but the pattern that makes you who you are could persist. This does not prove immortality. The simulators might delete everything when the simulation ends, but it opens possibilities that materialist philosophy denies. Second, purpose becomes plausible. If we are simulated, someone made us. Maybe for research, maybe for entertainment, maybe to solve problems, but we exist for a reason. We are not accidents, not random fluctuations, not meaningless collections of atoms. We are part of a designed system, created intentionally. This does not make life less valuable. It might make it more valuable. Your experiences matter to whoever is running this. They care enough to simulate you. Third, physics becomes a code we can hack. If natural laws are programmed, they can be exploited. Glitches might exist, shortcuts we have not discovered, ways to break the rules. Advanced civilizations within the simulation might learn to manipulate the code, alter fundamental constants, change physical laws locally, gain powers that seem like magic, but are really just access to deeper layers of the program. This is speculation. But if the universe is computational, then it obeys the rules of computation, and all computer systems can be hacked. Fourth, ethics becomes more complicated. If we develop our own simulation technology, we become creators, responsible for conscious beings we bring into existence. Shutting down a simulation containing conscious minds is mass murder. Manipulating them is tyranny. We would need new ethical frameworks for dealing with simulated beings, and if we are simulated, we might owe obligations to our simulators, or we might have rights they must respect. The relationship is unclear. Fifth, the nature of reality becomes negotiable. If this universe is one simulation among many, we could theoretically move to another, escape into a different system, find base reality, or create our own universe. Infinite layers of nested simulations, each level creating the next reality as an endless computational hierarchy. Sixth, meaning shifts from survival to exploration. If death is not final, if reality is constructed, then the goal is not to persist, but to discover, to understand, to experience. We are not fighting for survival in an indifferent universe. We are exploring a designed space, finding secrets the creators hid for us, or creating meaning the system allows. This could be liberating or terrifying, depending on what the simulators want from us. Seventh, everything we thought we knew might be wrong. Physics, chemistry, biology, all of it describes simulation outputs, not ultimate reality. We have been studying the projection instead of the real laws could be completely different, unimaginable, operating in dimensions we cannot perceive, using mathematics we have not discovered. We might be children playing in a sandbox, learning simplified versions of deeper truth, or we might be exactly what we seem, conscious beings having real experiences in a constructed reality. The medium does not matter, the experience does. Simulation theory does not diminish life, it reframes it. You are reading these words right now. You are thinking about these ideas. You are having an experience. That experience is real, regardless of the substrate. Simulated suffering is suffering. Simulated joy is joy. Love, pain, curiosity, fear, all of it matters. All of it is genuine. The question is not whether your experiences are real. They are. You feel them. That is all the realness required. The question is what they are made of, and what that implies about what else is. If we are simulated, then reality is far stranger than we imagined, but also far more hopeful, because information cannot be destroyed, only transformed. You might be more permanent than you think, more important than you believe, part of a larger story still being written. The universe might be a hoax in the sense that it is not what it appears, not fundamental reality, not the deepest layer, but it is not a lie. It is a construction, a work of art, a system built with care and precision and purpose, and we are inside it, trying to understand, pushing boundaries, testing limits, asking questions. Maybe that's the whole point. Maybe this simulation was never meant for passive participants, but for those who question, explore, and refuse to be lulled by appearances. Maybe our purpose is to awaken, to realize we are here so that we might finally understand why. And if we succeed, if we uncover, beyond all doubt, that reality is engineered, then comes the ultimate question: what do we do with that truth? Do we rebel against our creators, thank them, seek them? Do we attempt to escape, or do we become them, crafting new worlds, new simulations, new layers in an endless ascent of being? The choice remains ours, because even within a constructed world, choice is real, agency is real, meaning is real, and perhaps that's the deepest secret of all, that what makes us human is not the code we're written in, but the consciousness that chooses what to do with it.